Okay, so hello and welcome back. So in this video I want to show you how you can use inductors in RC circuits, and so there are a couple of things that we have to cover here. So first of all, so basically the first thing that we have here, in the previous circuits that we had these voltage divider circuits, or filter circuits that we constructed using a capacitor and a resistor, for example. So we had, for example, something like some signal coming in here in a resistor, and then we had some capacitor over here, the capacitor going to ground, and then this was, for example, V of out, this was, for example, V of in, this was a resistor, and this was a capacitor, and this was either a low pass filter or a high pass filter, and then that way basically it was basically also a voltage divider circuit for an AC signal. So now you can use inductors in basically instead of a capacitor over here. You can actually use an inductor in order to make something similar to the circuit that we have here, and that would basically look like something like this. So for example, you would have an inductor like this, and then this would be a resistor. The resistor would go to ground, and then you would have this V of out over here, and then you would have this V of in over here, and then this would be an L, or inductor, and this would be an R, and this would be called an RL circuit. Okay, so this RL circuit, the same with RC circuit, it has something called the there is something called the impedance in this circuit, and you know about the impedance. It's basically denoted by Z, and there is also a reactance in this circuit, and since the reactance is related to the inductor, it's denoted by X of, instead of X of C, you write it as X of L. And there is also the and that's basically that. Okay, so then in this particular circuit that we have here, your Z is going to be equal to the square root of X of L whole squared plus R squared. Okay, because you have a resistor over here and you have an inductor over here, so your impedance is going to be the square root of X of L squared plus R squared, and and X of L, the way that you can calculate that is X of L is equal to 2 pi FL. 2 pi times the frequency times the inductance of your inductor. So it's actually very simple. So now if you want to calculate, for example, the voltage output, so for example, for some circuit like this, so for example, let's say that you have some voltage coming in here, V of in, and then you have You have some inductor over here. This inductor going to a resistor, and this resistor is going to ground. And let's say that this is your V of out here, and this is your L, this is your R. So the output voltage that you can, the V of out basically over here, the V of out would be equal to so you're basically reading the voltage across this resistor. So that would be R over the impedance in this circuit, which is Z times V of in. Okay, times V of in. And if you had a circuit, for example, if you had the circuit like this, and if R comes first, you would have a circuit like this. So you would have a resistor over here going to an inductor. Okay, and then the inductor goes to ground, and if this is your input voltage and this is your V of out, if this is your V of out, then you are actually taking the voltage across the same inductor, as opposed to taking the voltage across the resistor. So here your V of out would be instead of R over Z would be the resistance of this inductor in this AC circuit, which is basically the reactance of this inductor, which is basically X of L over Z over the impedance times V of in. So it's very simple. The same thing as capacitors, and then basically the same thing that we have had before. Now, so for example, now if you have a circuit that has for example something like this. Let's say that you have a circuit, you have some input voltages, this comes to some inductor over here, and this inductor goes into some resistor over here. The resistors don't look nice today. And this goes to ground. This is your V of in, and this goes to V of out. This is actually your V of out, and you're reading the voltage across the resistor. And let's say that the voltage that comes in here is actually some voltage. Let's say that this is the 0 reference line on your on your oscilloscope, and then let's say that this is for example 10 volts on your oscilloscope, 10 volts, and this is for example 9 volts. This is 9 volts, and this is for example 11 volts over here. Okay, so and then now you have a signal like this. So how you would read this signal is basically you have a positive 10 volt DC offset, positive 10 volt DC offset, and then your signal is basically 9 to 11 is 2 volts peak to peak. So your AC voltage is 2 volts peak to peak. That's what the signal that is coming in. And of course the frequency depends on the period of your signal, but this doesn't tell you much about the period. I mean, if they told you that, for example, this is, for example, this period, this time period over here is such and such seconds, and based on that you could actually calculate the frequency. But usually, for example, the frequency is given to you. For example, over here we have been told that the frequency is 1 kilohertz, and of course based on this you can always calculate the the period of your signal, meaning that if you know that your frequency is 1 kilohertz, what that means is that basically if f is equal to 1 kilohertz, which is equal to 1000 hertz, then the period of your signal is 1 over basically 1000 hertz, 1 over 1000 hertz, which is equal to 0.001 seconds. In seconds, your period is in seconds. So that's 1,000th of a second, which is equal to 1 millisecond. This is equal to 1 millisecond. So what this means is that if you have a signal with a frequency of 1 kilohertz, which is equal to 1000 hertz, that signal has a period of 1 millisecond. That means that a complete cycle of that signal is occurring in basically in 1 millisecond, and that is one period of this signal, meaning that your signal is going up and down here, and then down and up, and then that is one complete basically one complete period, and that happens in 1 millisecond. So this is 1 millisecond, which is 1,000th of a second, and the same thing keeps happening over and over again. So, but we have talked about this before, and you must know it already. If we haven't, I don't know if I have or if I have not, but that's basically what that means. And let's say that your L over here is 160 millihenry. 160 millihenry. So the unit of inductance is Henry, and 1 Henry is usually a whole lot of inductance, and usually it's usual inductors are usually basically measured in millihenry or microhenry or something like that. Usually 1 Henry is a large amount of inductance. Okay, and let's say that this resistor over here is 1 kilo ohm. Okay, so now what you want to do, you want to calculate the output voltage over here. Basically what you want to do, you want to calculate the DC output voltage. So in order to calculate the DC output voltage, what you do in this circuit is that basically you see that if you assume that DC is coming in, then you see that basically DC is going into this DC is going into this inductor over here, and inductors are usually, the resistance of an inductor, if you take for example a multimeter and measure the resistance of an inductor, is usually very, very low. In like for example in like 1 ohm or 1.5 ohm or something like that, usually not over 1 or 2 ohm basically. So usually you can actually ignore them in DC circuits, because a 1 ohm resistor, it would act like a 1 ohm resistor in a DC circuit, and there is not much voltage drop across a 1 ohm resistor in a DC circuit. So you usually ignore that. So when DC is coming in, you have your signal coming in over here, and then you have a resistor, and that resistor goes to ground, and that is your R. Your inductor is simply not there, and this is your V of in, and you're actually reading the voltage across the power supply. So whatever you have in your input, which is 10 volts over here, you're getting at your output. So V of in is equal to 10 volts DC. Your output is equal to 10 volts DC. The same thing. Okay, so basically, so now you want to basically the output voltage over here would be 10 volts as the input voltage, meaning that, and if you want to use the voltage divider formula, it's basically V of out in a DC circuit. It's going to be equal to R to basically the resistance over here, which is R, over the total resistance in the circuit, which is again R times V of in. That means that V of out is equal to V of in, and that's basically your whole that basically means that your output voltage is the same thing as your input voltage. Now in this circuit, if you want to find the reactance of the inductor, the reactance of this inductor is going to be equal to X of L is equal to 2 pi FL, which is equal to 2 pi times the frequency. So the frequency was 1 kilohertz, so 10 raised to the power 3 hertz times the inductance of your inductor, which is 160 millihenry. 160 millihenry is 116 to 10 raised to the power negative 3 Henry, and that's equal to 2 pi times 160, which is equal to 1005.3 ohm, basically. Okay, so that is that, and now if you want to find basically the output voltage over here, the AC output voltage, the AC output voltage, so basically what you're doing is that you're monitoring the voltage across this resistor, and so the voltage at that point, V of out, which is equal to V of R, is equal to the resistance of that resistor divided by the total resistance in this circuit, which is actually the impedance in this circuit. So divided by R divided by Z times the input voltage, and that's equal to, so for that basically you need your impedance, and we said that basically your impedance is equal to the square root of X of L squared plus R squared which is equal to the square root of X of L was equal to 1005.3 squared plus R squared, and your R was 1000 ohm or 1 kilo ohm squared, and that's equal to the square root of 1005.3 squared plus 1000 squared is equal to 1417.97. 1417.97 basically ohm. Okay, now that is your impedance. So your V of out is going to be equal to R to Z, which is equal to 1000 ohm to Z, which is basically 1417.97, for example, times V of in. And since you're calculating the AC output, you have to take care of your output here, which is basically 9 to 11, so that's 2 volts peak to peak. So times 2 So that's equal to 1000 divided by 1417.97 times 2 volts times 2 volts, which is equal to 1.41 volts. 1.41 volts peak to peak. Okay, so that's your output voltage, and that's basically all that you need to know about this. You need to know about this circuit. Now, if you want to do if you want to show what sort of output signal you're going to have as a result of this circuit, is that your input signal was basically something like this. So let's say that you had let's say that this was basically or let me do it like this. So this was basically 0 volts, and then you had 10 volts up here. You had 10 volts up here, and then you had 9 volts over here, and basically 11 volts over here, and this was your waveform of the input. So that was basically 2 volts peak to peak, 2 volts peak to peak. V of PP was equal to 2 volts peak to peak, and so there was a DC offset plus 10 volts offset DC. Okay, so that is basically your input. Now your output. So now here we said that the DC output was again the same thing, 10 volts DC, and the AC output was 1.41 volts peak to peak. So now the DC V out was equal to 10 volts DC, and AC V out was 1.41 volts, 1.41 volt peak to peak. Okay, so now what that means is that you have again 10 volts offset. So you have basically the same. Let's say that this is the same reference line over here, 0 volts here, and then you have the same offset voltage, 10 volts. So that is basically your 10 volts there. And then basically your peak to peak voltage has changed from 2 volts to 1.41 volts, meaning that when your peak to peak voltage is 1.41 volts, then that means that half of that would be equal to 1.41 divided by 2 is equal to 0.705. So you have to add 0.705 to basically to the top of this line to get the peak voltage over here, and again another 0.705 volts down here in order to get the peak voltage down here. So then 0.705 plus 10 volts is equal to 10.705 volts. That means basically that's going to be 10.705 volts over here, and down here it's 10 minus 0.705, which is equal to 9.295 volts over here, and then that's going to be your output, for example. Okay, so that's basically what's your basically your input and output. Now what happens here is that there's going to be some phase shift over here depending on the type of the circuit that you have, and there are basically these two types of RL circuits, And in these RL circuits, depending on whether your inductor comes first or your resistor comes first, it's going to be either a low pass filter or a high pass filter, but we will talk about that later when we get to phase shift in these circuits. So that's basically this circuit over here. Now now let's do another one of these examples. So now in this circuit over here, the difference is that basically the inductor is a pretty large inductor. I mean, as far as the ohmic as far as the ohmic value of the inductor is concerned, it has a resistance of 500 ohms. So you cannot neglect the resistance of that inductor in the circuit. So now you have this circuit over here that comes into an inductor, and then that goes into a resistor over here, and then your resistor is grounded. So this is your R, 1 kilo ohm, and this is your L, 320, for example, millihenry, and the resistance of this inductor is 500 ohm. Okay, and this is your input voltage V of in. Now the input over here is like this. So you have a signal coming in like this, and this is 10 volts. This over here you have 12 volts, and over here you have basically 8 volts. So that's basically 4 volts peak to peak. 4 volts peak to peak. And the frequency is 1 kilohertz. And that's basically the circuit that you have. So you want to, and this is over here, this is your V of out. Okay, so now in this circuit you want to calculate the DC output and also the AC output of this circuit, and also draw the output waveform of the circuit. So that's basically this one. Now I'm talking about these because I wanted to actually I wanted to build a circuit for testing inductors, and without the theory that we have here, we would not actually understand how that circuit would work. So that's basically why I'm talking about these. And of course, these basic things about inductors and high pass and low pass filters are actually going to be needed everywhere in the AC circuits. But before I go any further, I take a few minutes rest, and I'll be back with you with the rest of this. Okay, so now in this circuit, what we have is basically this thing over here, and get rid of this paper over here. Okay, so basically we want to first let's go through the DC output of this circuit. So the DC output would be, so basically if DC comes in, you have this inductor over here and this resistor, and this becomes a simple voltage divider circuit, and there would be a 500 ohm resistor here, a 1 kilo ohm resistor here, So then V of out, actually that would be DC V of out. Okay, that would be DC V of out. V of out is equal to basically R over the total resistance in this circuit, which is basically R plus lowercase r, which is the resistance of that inductor, times V of in. Now you see that there is an offset of 10 volts on this signal. That means that DC V of in is equal to 10 volts DC. Okay. So so then the value of your resistor is basically 1000 ohm. The value of your resistor, again, 1000 plus 500 ohm, the resistance of that inductor, times V of in, which is 10 volts DC. So that's the same thing as 1000 over 1500 times 10, which is equal to 10 to 15 times 10. So 1000 over 1500 times 10, that's equal to 6.667. That's equal to 6.67 volts DC. That's your DC output. Now, for your AC output, AC V of out, you have basically for your AC output, you're basically monitoring the voltage across this resistor, which is the resistor over the total resistance in this circuit, which is, when AC comes in, this becomes impedance. So R over Z times V of in. So your Z is equal to the square root of X of L squared plus R squared. And your X of L squared, or your X of L, is equal to 2 pi FL. 2 pi FL. So this is equal to 2 pi times F. The frequency was basically 1 kilohertz times 1000 hertz times L, which is 320 millihenry. 320 into 10 raised to power negative 3 Henry. So these two you can cancel out, and then you have 320 times 2 pi. 320 times 2 pi is equal to 2010.6. 2010.6, and that's in ohm. That's the actually the reactance of the inductor at the frequency of 1 kilohertz. So now your Z is equal to the square root of X of L squared, which is 2010.6 squared plus R squared, which is equal to 1000 squared. So this is equal to the square root of 2010.6 squared plus 1000 squared, which is equal to 2245.55. 2245.55 ohm again. So now that I have X of L and Z, I can calculate AC out. So AC V of out is equal to R over Z. So my R was basically 1000 ohm over Z, which is 2245.55 ohm, times V of in. And my V of in AC voltage was basically 4 volts peak to peak, times 4 volts peak to peak. So that is equal to 1000 over 2245.55 times 4 volts peak to peak, it gives me 1.78 volts peak to peak. 1.78 volts peak to peak. Okay, so that's your AC output. And now that you have all of these values, the output waveform of this circuit is going to be something like this, meaning that you would have your DC offset, your DC offset, your DC out V of out, your DC V out is equal to 6.67 volts DC, and your AC V of out is equal to 1.78 volts peak to peak. So since your peak to peak voltage is 1.78 volts, if you divide by 2, 1.78 divided by 2 is equal to 0.89 volts. So AC V of out is equal to 0.89 volts peak. So that's the peak voltage, which is half of the peak to peak voltage. So then what I can do is that I can put my signal over here, and then the baseline for this signal is going to be, instead of 10 volts, is going to be 6.67 volts DC, which is my DC offset, 6.67 volts. And then my peak voltage is 0.89 volts peak. So if I add 6.67 volts, plus 0.89 volts, which is the peak voltage, 0.89 volts, it's going to give me 7.56 volts, which is, let's say this is over here, 7.56 volts. And the same voltage, 6.67 volts, minus the peak voltage for the lower peak, is 0.89 volts, and that is the same thing as 5.78 volts. 5.78 volts, and that's going to be the shape of my signal over here. So this is my input and this is my output. Okay, so that's basically all. Now the next thing that we have here is and there is one thing that you need to pay attention to here, and that is in order to basically in order to calculate V of out, the AC voltage, in order to calculate V of out here, AC V of out, that was equal to basically, for example, something like R over, for example, Z times V of in. And Z was equal to basically the square root of X of L squared plus R squared. Okay. Now X of L was equal to 2 pi FL. Okay. So that means that as you increase your frequency, then of course your reactance is going to be increased. There is a direct relationship between the frequency and the reactance of your inductor. And as that increases, as the reactance increases, so does the impedance of your circuit. and then with that basically your V of your AC V of out is going to be decreased because your Z is in the denominator here. The more that you increase your Z, the more you're actually decreasing your V of out. Okay, so basically X of L here changes with frequency of the input signal, and then the amplitude of this output voltage changes with frequency as well, meaning that the higher the frequency, the lower the amplitude, and the higher the frequency, the lower the amplitude of your output, and then the lower the frequency, the higher is going to be the amplitude of your output. And if you basically do a plot of this phenomenon over here, meaning that if you take this as F of in and V of out, you are going to get something like this. You're going to get something like this, and there's a point over here, for example, somewhere over here, where your voltage starts falling or decreasing very sharply, which is basically, let's take it as this point arbitrarily, and you can take this point as, for example, you can take this as F1, and there is some place over here, somewhere over here, where you can call it F2. This is F of in, where you can call it F2, where your signal kind of levels off. So these two frequencies you can, and then of course this is, as you can see, this is of course connected to some sort of slope in this voltage versus frequency graph. So this is slope, and actually where this point actually begins and where it stops, and the whole thing you can control by changing the values of your R and L in your circuit, meaning that you can play with your R and with L in such a way that for example you can move this point a little bit to the left or to the right, or you can move this point to the left or to the right. And also there are some ways to change the slope of this line, meaning how sharply you get from this point to this point. Okay, and of course we are going to get there, how to basically control this thing over here. So okay, so now as another example, let's have another example here. As another example, and of course I'm going to summarize all of this in one, basically in one, when we get to the phase shift, I'm going to summarize all of this, then you will have a better, overall understanding of this whole thing over here. Okay, you don't need to worry if you didn't understand this pretty well. And then basically so far the circuits that we had were basically you had your inductor over here, and then you had the resistor over here, and the resistor was grounded, and this was your V of out, and this was your V of in, and then we got a basically a graph like this, meaning that the graph of V of out, meaning that the graph of this, if you take this as F of in and V of out, the graph of V of out versus frequency, since you're monitoring the voltage drop across this resistor, what happens is that as you increase your frequency, the reactance of this inductor is going to increase, and more and more voltage drop is going to occur across this inductor, and then so the higher the voltage drop across this inductor, the lower the voltage drop across this resistor. So that means that the more that you increase your frequency, the less is going to be voltage drop across this resistor. So that means that your voltage is actually going to drop down as you increase your frequency. Then that's going to be the way, I mean, the graph of this circuit over here, and that's actually a low pass filter. That's a low pass filter. Okay. Now you can also have the inverse of this whole situation, where you have your resistor up here and your inductor down here, meaning that your signal comes in here, then you have your resistor, then you have an inductor over here, and that's basically your circuit over here. So this is your R, this is your L, and this is your V of out, and this is your V of in. Now what happens here is that as you increase your frequency, the reactance of this is going to increase as well, because you know that X of L is equal to 2 pi FL. So there is a direct relationship between frequency and reactance here. So more reactance means more voltage drop across this inductor, and so the higher is going to be the voltage at this point. So then you're going to practically get something like this over here. Okay, so if that is V of out and this is F of in, that's going to be the graph of this circuit, V of out versus F of in, and that's going to be a high pass filter. That's going to be a high pass filter. And then if you want to, for example, in this circuit, if you want to calculate the voltage, the output voltage here, V of out, is going to be equal to the voltage across basically the inductance of, the reactance of this inductor, which is X of L, over the whole, basically the total resistance in this circuit, which is impedance when AC comes in. So X of L to Z times V of in. That's basically how you can calculate the output in this voltage, in the output in this circuit. And then there are some other things like there are basically some terms that we can also talk about. For example, we have something called the first order filter. We have something called 8th order filter and so on, 5th order filter and so on and so forth. And what that means is that basically a filter circuit normally contains either a capacitor or an inductor or an op-amp. So you can have if you want to build a filter, you either do it with a capacitor. You either do it with a capacitor or you do it with an inductor, or you do it with an op-amp. We will talk about op-amps in later videos that we are going to do, but so basically if you build a filter that basically in which you have basically one capacitor or one inductor, that's called a first order filter. That's called the first order. That's called the first order filter. Okay. And then the filter order numbers, for example, first order, second order, and so on and so forth. The filter order numbers reflect the number of capacitors or inductors or op-amps, operational amplifiers, that you actually use in those filters. For example, if a filter contains, for example, four capacitors, if you have in a filter, then that filter is called that filter is called basically a fourth order filter. A fourth order filter. Okay. Or if you have, for example, 6 capacitors in a filter, that would be called a sixth order filter, and so on and so forth. Okay. And actually with these filters, what you can do, I mean, it's actually important to note that I basically over here, when we talked about F1 and F2 in this graph, we said that by playing with the values of R and L, you can actually move these 2 points around. You can actually, if you move these points around and if you imagine that these points are actually hinged to or connected to these points in the graph, when you move them around, your graph is going to be deformed, right? The graph is going to change the shape of itself. So by playing with the values of R and L in your circuit, then what's going to happen is that you're going to actually move this thing around. Now, one thing that you can do is that basically you can the slope of this line, you can actually control it by the order of the filter that you use, meaning that for example, the more capacitors, for example, that you use in your filter, the more, I mean, a higher slope you are going, a higher negative slope actually you're going to have. For example, this is actually a negative slope here, right? So a higher negative slope you're going to have in your graph, and that basically means that the sooner you're going to get from this, for example, from this output to this output over here. Right now, to get from this output to this output, it takes this span of your frequency, but then you can change that, meaning that if the slope of this line was if this line was actually a little bit steeper, then you would get something like this, and then it would take you, for example, this span of your frequency to get from this output to this output over here. Okay, so that's basically what you can do with these. I mean, we are not going to play with this, but we are going to be playing with some inductors, and actually what I'm going to do is that after once we are done with these videos on inductors, I'm going to build a circuit in order to test the value of some inductors, because I need an inductor meter and I don't have it. I want to build one so that we can use it with an oscilloscope. We can actually measure the value of inductance in an inductor. So that's basically this. And then the next thing that we have is a couple of things about phase shift that we will do in the next video, and then we will be done with the theory part of these filters, so or these inductors. So I'll see you in the next video. Thank you.